Hello, I am Jasmine Batra. I will be explaining question 1 of homework 10 from probability and stochastic process. In this question 1, they have asked to collect the definition and simple properties of examples of stochastic process. First one is the Poisson process. A Poisson process is defined by the following properties. Firstly, the number n of t1 comma t2 of point t1 in the interval t1 comma t2 of length t is equal to t2 minus t1 is a Poisson random variable with parameter this. Probability of n of t1 comma t2 is equal to k is equal to e power minus lambda into lambda t power k by k factorial. Second of this is if the interval t1 comma t2 and t3 comma t4 are non-overlapping, then random variables n of t1 comma t2 and n of t3 comma t4 are independent. Third part of this is at the time moment t there is no more than one Poisson property. Using the point t I, we have the stochastic process x of t is equal to n of 0 comma t. This is the following curve we get. And second, first order probability mass p of x of t is equal to k is equal to e power minus lambda t of lambda t power k by k factorial. So mean we get is lambda t, autocorrelation we get is lambda square t1 comma t2 is plus lambda minimum of t1 comma t2, autocovariance is lambda minimum of t1 comma t2, and thus we can conclude the mean of Poisson process is lambda t, which is a linear function of t. It matches our the autocorrelation function contains term minimum of t1 comma t2, which comes from property of independent increment. Second part we have to explain is Poisson increment process, which is defined as x of t plus epsilon minus x of t by epsilon, where x of t is Poisson process. First order probability is e power minus lambda epsilon into e lambda epsilon by power n by n factorial. So mean we will be getting as lambda. Autocorrelation function is lambda square, where mod of t1 minus t2 is greater than equal to epsilon, and lambda square plus lambda by epsilon minus lambda mod of t1 minus t2 by epsilon square in the condition t1 minus t2 less than epsilon. The autocovariance is 0 for t1 minus t2 mod greater than epsilon, and lambda by epsilon minus lambda into t1 minus t2 by epsilon square when t1 minus t2 mod less than epsilon. Thus we can conclude that Poisson increment process is introduced to prepare us to define the Poisson impulse function, and thus it creates a triangle with area lambda which is independent of epsilon, and when epsilon goes to 0 the triangle becomes impulse with area lambda. And for the third part, Poisson impulse process is defined as z of t is equal to dx of t by dt, which is thus we get a following curve. Mean is equal to lambda, autocorrelation is equal to lambda square plus lambda into t1 minus t2, autocovariance is equal to lambda sigma of t1 minus t2. Thus we can say the process z of t minus lambda has mean 0 and autocorrelation as above stated. We may define it as output of the linear time invariant system with the impulse response h of t and the input as in a Poisson impulse. Fourth part is semi-random signal is defined based on the Poisson points. Again, the number n of t1 comma t2 of point ti in the interval t1 comma t2 of length t is equal to t2 minus t1, where probability of this function is defined as e power minus lambda t into lambda t by power k by k factorial. So first order probability is given by this equation. Mean we get is e power minus 2 lambda t, autocorrelation function is e power minus 2 lambda mod of t1 minus t2, and autocovariance is e power minus 2 lambda mod of t1 minus t2 minus e power minus 2 of t1 plus t2. So probability of x of t is equal to 1 is not half because we start with 1. So when probability of x of t is equal to 1 should be little higher than half. So it goes to half when goes to infinity, which matches our expectation. So expectation of x of t is equal to e power minus 2 lambda t goes to 0 when it goes to infinity, which matches our expectation as well. That match when t1 comma t2 are far away, x of t1 comma and x of t2 are less correlated. Fifth part is random telegraph signal. So x of t is equal to a of x of t. Probability of a is equal to 1 is equal to probability a is equal to minus 1 is equal to half, and x of t semi-random telegraph signal. Mean we will be getting a 0. Autocorrelation is equal to e power minus 2 lambda mod of t1 minus t2. Covariance is e power minus 2 lambda mod of t1 minus t2. So probability of I of t is equal to 1, which is equal to probability of I is equal to t is equal to minus 1 is equal to half. This makes us given that y of t may be strict sense stationary. Expectation of y of t is a constant also makes us given. So the sixth part we have to explain is random walk. Suppose we have to toss a fair coin n times. K is the number of times of head on n toss. X of n of t is equal to ks minus n minus k. So mean we will be getting 0. Autocorrelation, expectation of x of n t into m t is equal to minimum of n comma m s square. Autocovariance is minimum of n comma m s square. So from the probability mass we given that when n goes to infinity we will have the Gaussian density. The autocorrelation contains the term minimum of t1 comma t2, which comes from property of independent increment. Sixth one, linear process, which is limit x t tends to infinity, s by t square tends to a, and n tends to infinity, where x of t is random walk. First order density is given by this equation. Mean will be getting 0. Autocorrelation is minimum of t1 comma t2 alpha. Autocovariance minimum of t1 comma t2 alpha. From this we can conclude that w0 is equal to 0. W has independent increment. W of t plus u is equal to wt is independent of sigma ws, that's s less than equal to t. W has Gaussian increment. W of t plus u is equal to wt is a normal distributed with mean 0 and variance u. W is a continuous path with probability. Wt is continuous in t. Thank you.